So in this lecture, we'll look at the second application of double integration, the dynamics of rotating objects. So things like axles or rotors or frisbees or acrobats. Now, as we'll see, we can boil a lot of those dynamics down to two simple concepts: the center of mass and the moment of inertia. Now, we'll get to those concepts in a moment, but in the meantime, what you should try and remember in this lecture is that we're going to be calculating some double integrals, and we're going to have to use a lot of the skills that we've learned so far in this topic. So sketching regions of integration, making use of limits, using polar coordinates, and especially making use of any symmetry in the problem to simplify our integrals as much as possible. So in this course, we're going to be focusing on the dynamics, the center of mass, the moment of inertia, of thin, flat objects. So think about a tile or a plate or a frisbee, something that's quite thin and has some extent in the x and y direction, but a negligible thickness in the z direction. So we're going to call those laminas, and the reason we're focusing on those is because the integrations that we're going to have to do are going to be a little bit simpler. Of course, those ideas extend to three-dimensional objects, and we can easily extend these ideas to objects that have some sort of extent in the z direction but have uniform cross-section. So again, just thinking about here two-dimensional objects, thin, flat objects, or objects that are extended in the z direction but have a uniform cross-section. And again, these ideas do extend to three dimensions very easily, just the integrals become a little bit more complicated. So the first idea that we have to introduce is the mass of an object. So thinking about how that mass is distributed in the object, we might have some sort of object, for example, something like this, flat object here, where maybe there's a whole bunch of mass at this end. And you can see that I could kind of hold my object in the middle, but because there's so much more mass over here, it would start to tip that way. So I want to find, where do I hold this object if there's a whole bunch of mass at this side? So I'm going to hold it more closely to where the mass is located. So we call this location, where I can sort of hold onto this object and it's not going to tip or back or forth, we call that the center of mass of the object. It allows us basically to describe all of the mass in the object at that one point. So it really simplifies calculations involving much more complicated situations. Now, if the mass is uniformly distributed throughout the object, that is, it has a uniform density or constant density, then the center of mass will be the same as the center of the object. And when I say the center of the object, I mean the geometric center of the object. So we call the geometric center of the object the centroid. That's where basically the shape has its center. It doesn't have to be the same as the center of mass, but it will be if the mass is uniformly distributed. Of course, more generally, if I have a more complicated distribution of mass, a more complicated density, then the center of mass will not be the same as the centroid. So let's have a look at how I calculate the mass of an object using a double integral, and how I can calculate the center of mass, where all that mass can be thought of as being. So the density of an object in a lamina, so thinking about a two-dimensional object that depends upon x and y, but not on z. So we're going to describe the density, delta, as basically the amount of mass per area. So if I have the mass at a particular location is going to be given by the density times the area, where I've got some infinitesimal area and infinitesimal mass, then the relationship between those two things is dm is the density times the area. So just if I drew a little picture of what I mean by that, we could imagine that I've got some little tiny square inside of my complicated object. The area of that square is dA. I know that the density at that location is given by delta xy, that is the kilograms per meter squared or whatever. Then the mass is just the product of those two things. So the mass, the infinitesimal mass of this tiny little square of stuff, is going to be given by the density multiplied by the area. Okay, so I've got a bazillion tiny little squares like this, I'd like to find the total mass, so I'm just going to add up the mass of each of those squares. And of course, when I'm adding up something where there's infinitely many, I'm actually doing an integral. So the total mass of my object is going to be given by the integral over omega of the density times the infinitesimal area. Now, omega here is actually going to be the region of integration, which will be the actual object. It'll be the shape itself. So for example, if I've got some funny looking object like this, a bean shape, my region of integration is the shape, and then I'm going to add up a whole bunch of little tiny squares within that shape to calculate what the total mass is. So I could add up, this shape has got an area A, it's got a density delta xy at every point in x and y. I know what the mass per unit area is, and I know that the infinitesimal element, that little tiny square there, has a mass of delta m. So all I have to do to calculate the total mass is add up all of those little tiny masses. Alright, so now I'd like to be able to express where the center of mass is of that object. And the way I'm going to do that is by thinking about how is that object responding to sort of tipping over. So if I was to place my finger at a particular point, would this thing tip over? So how do I measure that? Well, I do that using something called the first moment. You can think about that as a little bit like the lever force. So if I imagine setting up a little seesaw, let's draw a little seesaw here like you'd find in a kid's park, and imagine I've got a little a plank on top of this fulcrum, and I place a mass on this seesaw. So here's my mass. Let's give it an amount m. That's the mass of that object. You can see that placing that mass there is going to tip this thing over. Now the question is, how much does it tip it over? Well, that's going to depend on two things. It's going to depend on how much mass I place there, how big m is, but it's also going to depend on how far I place this thing from the fulcrum, right? The further I place it from the fulcrum, the greater that lever force. So I can increase the lever force either by increasing the mass or by putting it further away from the fulcrum. So what is this lever force? Well, we're going to refer to this as m subscript y, so big M subscript y, equals to the distance by the mass. So the distance from the fulcrum is x, and the mass is m. Now let's think about that. Why did I put a subscript y there? Well, the reason I put a subscript y there is because this is the lever force for rotations about the y direction. So the way that I set up this coordinate system, x is pointing in this direction and y is coming out of the page. So when I talk about a lever force, I'm talking about rotations about the y-axis. So that this little subscript y there is telling us the axis of rotation. Now that lever force is going to depend on the mass. The larger the mass, the greater the lever force. That makes sense. But also, the further out I put this mass along the seesaw, the greater the lever force as well. So we call this the first moment of mass about the y-axis. Now, imagine now that I have not just a single mass, but I've got a whole bunch of masses, a whole bunch of little infinitesimal masses. So what would that look like? In that case, I would be replacing my single mass with a whole bunch of little ones. So again, I've got a little seesaw here, and I'm placing lots of little infinitesimal masses, each with a mass delta m. Let's call this one with delta m, and a distance x from the origin. So you can see that each little infinitesimal mass will have a moment, a first moment of x times delta m, the mass times the the distance, and I'd like to be able to calculate the total first moment, and that's going to just be the addition of all of those little moments. So I'm basically going to do a double integral over my object omega. Now we know that delta m is given by the mass is given by the density times the area. So I can express the first moment as a double integral. So I've written it down here for you. The total first moment will be the integral over all of those infinitesimal masses. So total, adding up all of the first moments from each of those masses, integrate over my object omega, and I end up with the first moment. And you can see this is the first moment about the y-axis, so the rotational force about the y-axis is given by the distance along the x-axis times the density times the infinitesimal area. And the corresponding first moment about the x-axis will be the integral of the moments about the x-axis. So these are the little infinitesimal moments about the x-axis, and we can write that as a double integral over the region, over the object itself, omega, of y times delta xy. So y here is the distance along the y-axis. So we have to be a little bit careful here when we're thinking about the moments of inertia, the first moments here. These are the rotation moments, because the notation can be a little bit tricky in the sense that we've got an m subscript y here is given by the distance along x, and m subscript x here is given by an integral over y times delta xy. So it's sort of the opposite of what you might think initially. We just have to remember that that subscript is referring to the rotation about the x or y axis. So let's draw a little sketch here of what it might look like for a two-dimensional object. Again, let's draw a sort of funny looking beam thing. I'm setting up two axes. Here's my axis in the x direction. Here's my axis in the x direction. Here's the axis in the y direction. I have some sort of distribution of mass that's given by delta xy. That's the density at each location as a function of x and y. I'd like to know what is the rotation due to this tiny little mass here, delta m, about the x-axis and about the y-axis. And so I can calculate that if I know how far it is in the x direction and how far it is in the y direction from the corresponding moment, from the corresponding axis. So this now allows us to think about where should I put the origin, where should I put my cross here, so that this thing actually doesn't rotate at all, right? So if I could figure out exactly where to balance this object, where would I need to put the center? And that is exactly the center of mass. So basically what we're imagining is that we're replacing this complicated object here with a single point. So again, here's my x and my y axis. I'm replacing this complicated object with a single mass. Let's call it big M. That's the mass of the total mass of my object. And it's at coordinates. We're going to call them x bar and y bar. Those are the center of mass coordinates. So I can replace this entire object here, this complicated lamina, with a single point that has the mass of that lamina. This lamina here is a total mass of big M, and it's located at coordinates x bar and y bar. And what the significance of that is that I can basically suspend or hold my object at that point, and it has no rotation in either the x direction or the y direction. So how do I calculate what that point is? What are the center of mass coordinates? Well, what we're going to do is we're going to imagine putting all of the mass at that location and then calculating the corresponding first moment. So we can see that the first moment of this point mass about the y-axis is given by the distance in the x direction times the mass, and that has to match the corresponding first moment of this object. We can do the same thing for the y-coordinate, and you see that what we're going to get is these equations. So I have that the x-coordinate is given by 1 over m times this integral, so that's the integral, this actually is the first moment about the y-axis divided by m, and the y-coordinate will be the first moment about the x-axis divided by m. So again, we're basically asking, if I could just replace this whole object with a single point mass located at a distance x bar from the y-axis and a distance y bar from the x-axis, what is the value of x bar, what is the value of y bar, that would give me the same first moments as this object, same lever force. And that's what's given by these expressions here. So you notice here that when I'm calculating center of mass, the center of mass coordinates x bar and y bar, I'm going to have to actually calculate a number of double integrals. I'm going to have to calculate the mass, that's the double integral over the density. I'm going to have to calculate the first moment about the y-axis and the first moment about the x-axis. So those are also double integrals over the density and the distance from the y-axis or the distance from the x-axis. So that is the center of mass. The second important concept that we need to introduce is the idea of a moment of inertia. And the moment of inertia tells us the resistance of an object to rotation. Now clearly some objects will rotate more easily than others. If all of the mass of the object is located very close to the center, then it's very easy to spin that object around. If all of the mass is located far away from the center, it's much more difficult to rotate that object. Just in the same way that an ice skater can change their rate of rotation by pulling their arms in, they're basically reducing their moment of inertia, or extending their arms out, they're increasing their moment of inertia. So they're increasing or decreasing their resistance to rotation. So what quantifies that is exactly the moment of inertia. So the moment of inertia is given by the mass of the object times the distance squared. So you can think of this as the moment of inertia is x squared times m. So if you increase the mass of the object, yes, absolutely, it increases the moment of inertia, but you can actually increase the moment of inertia even more efficiently by just moving that object or moving the mass a little further away from the axis of rotation. So how do I calculate the moments of inertia? Well, again, we're going to be setting up some double integrals. So thinking about the moment of inertia about the x-axis and the moment of inertia about the y-axis, that is the resistance to rotations about the x-axis and the resistance to rotation about the y-axis. Those are going to be given by the distance squared from the x-axis times the infinitesimal mass, or the distance squared from the y-axis times the infinitesimal mass. So you can see again we're going to have to set up some double integrals. The last type of moment of inertia that we'll have to deal with is what's called the polar moment of inertia. This tells us how hard it is to rotate an object about the origin, and so that's going to be given by the sum of the other two. So it's going to be given by x squared plus y squared delta xy. Now, I've set up those formulae for you, and they're given to you on the first page of these lecture notes, so we can refer back to them. But the important thing is that we're going to have to calculate a whole bunch of double integrals. So we're going to have to try and find ways to do those as efficiently as possible. Let's try and simplify those integrals. As you can see, as you're going to see, symmetry is going to be really important in allowing us to do that. So let's try and apply these formulae now. Let's look at an example. So we're looking at, in example 1, a thin plate in the first quadrant that's bounded by the coordinate axes and this line, x plus y equals to 1. So we want to find the mass and the center of mass that is the coordinates x bar and y bar, assuming that either the density is uniform or that we have a non-uniform density. So we're going to do these two one after another. So by the way, when we're dealing with something that has a uniform density, so the same mass per unit area at every point in space, then the center of mass that we get there will be exactly the same as the centroid. It'll be the geometric center of the object. So the first thing we need to do here is to sketch our region of integration before we can set up the appropriate double integrals. So let's sketch our region of integration. So we've got x and y. We've got the line x plus y equals to 1, or if I rewrite that, y equals to 1 minus x. So that's a line passing through y is equal to 1 with the slope of minus 1. So that's easy to sketch. It's something like this. Here's the coordinate axes. So the region of integration is clearly this region here. So let's set up the appropriate limits of integration. We're going to look at the points of intersection. So this point is x is equal to 1, y is equal to 0. This point here is x is equal to 0, y is equal to 1. And if I pick values of x between 0 and 1, pick values of y between 0 and 1 minus x, then my region of integration is going to be given by the following limits. X goes between 0 and 1, y goes between 0 and 1 minus x. Now what's nice about these integrals is that the region of integration doesn't change. We have to calculate a couple of different double integrals. The only thing that's changing though is the integrand. So let's start off by looking at the mass. So the mass was given by the formula integral over my region of integration, so integral over the object, of the infinitesimal mass dm. So if I have a uniform density, then dm is simply, remember that dm was given by delta xy dA. But if we have a constant density, so a density of just 1, then this is the integral that I need to do. So now let's set up my integral. Using those limits of integration we calculated. So x is going to be our outer integral, y will be our inner integral. And we can straightforwardly calculate this. So we're going to get the integral from 0 to 1 of y from y is equal to 0 to y is equal to 1 minus x. So this will give us 1 minus x minus 0, integrating with respect to x, gives us x minus x squared over 2 from 0 to 1, which will be equal to 1 minus a half minus 0, which is equal to a half. So the mass of this object is a half, and we're going to use that expression in a number of the formulae. So we've calculated the mass. Now let's look at the first moments, because we're going to need those to be able to calculate the center of mass coordinates. So the first moments that we're going to calculate are the first moment about the y-axis, which is the distance from the y-axis, so x dm, or x delta xy dA, and the first moment about the x-axis. So that's given by the distance from the x-axis, which is y. So y delta xy dA. So you can see we're going to have to set up two more double integrals. But again, the nice thing here is that the regions of integration omega are the same, so the limits of integration are the same. So setting up the integral m subscript y, so the first moment about the y-axis. So we've got, again, integral over x is the outer integral over y is the inner integral. Our integrand now is going to be x times delta xy, and delta, remember, was just 1. We're going to do y integral, then the x integral. So carrying out that y integral gives us x times y, from y is equal to 0 to y is equal to 1 minus x. So substituting that in is going to give us the integral from 0 to 1 of x times 1 minus x minus 0. So doing that integral over x gives us x squared over 2 minus x cubed over 3 doing the integral 0 to 1. So we have 1/2 minus 1/3 minus 0. Putting in x is equal to 0, we get nothing, which is going to give us half minus 1/3 is 3 over 6 minus 2 over 6, which is 1/6. So we have that the first moment about the y-axis is 1/6. Let's take a look at the corresponding integral about the x-axis. So this is the first moment about the x-axis. So this is going to be x times the, y times the density. And again, we're doing this integral over the same region of integration, so the limits of integration are the same. And we're going to get the integral from 0 to 1. Integral over y is going to give me y squared over 2. From y is equal to 0 to y is equal to 1 minus x dx. Substituting in those limits gives me integral from 0 to 1 of 1 minus x over 2, and that 1 minus x is squared. Take out that factor of 1/2. We're going to get 1 minus 2x plus x squared. Carrying out the x integral then is going to give me 1/2 times x minus 2x squared over 2 plus x cubed over 3. Get some cancellation. 2 and 2 go out. Putting in those limits, we're going to get 1/2 of 1 minus 1 plus 1/3. So the 1 and the minus 1 cancel out. We've got 1/2 of 1/3, which is 1/6. So we find that the first moment about the x-axis is 1/6. Actually, it's the same as the first moment about the y-axis. And we'll just gather together our mass as well. M is equal to 1/2. So for the constant density case now, we can calculate what the center of mass coordinates are. So the center of mass coordinate in the x direction is going to be given by the first moment in the y direction divided by the mass, so that's 1/6 divided by 1/2. So that'll be given by 1/6 times 2, which is 1/3. And we have the center of mass coordinate in the y direction, we call it y bar, is going to be given by the first moment about the x-axis divided by the mass, which is 1/6 divided by 1/2, which is also 1/3. So we find that the center of mass coordinates are the same. So we have 1/3, 1/3. Now, could we have predicted in advance that we would have this sort of matching, that the x-coordinate and the y-coordinate of the center of mass would be the same? In fact, we could have seen that using some symmetry. So if we go back to the sketch that we did at the beginning, you can see that this sketch is completely symmetric between the x and the y directions. I could actually swap the x and the y axes here and get exactly the same picture. So the region of integration here is actually symmetric between x and y, and that means that the x-coordinate and the y-coordinate of the center of mass have to be the same. Now, in this case, we had a particularly simple example where the density was uniform. Does this change when the density is non-uniform? So let's take a look at part B, where we have a non-uniform density given by x times y. So the integrals we're setting up are the same. The region of integration is the same. The only thing that's changing is the integrand. So this is part B. And in this case, we're looking at a non-uniform density, a non-constant density, given by x times y. So I'm just going to write down my integrals, and hopefully they'll go nice and quickly. We've got the integral over the density times the area. So my region of integration is the same, so the limits of integration are the same and the order is the same. My density has changed now, so the integrand is different. So this is the double integral I need to calculate for the mass of this non-uniform density object. So we've got the integral from 0 to 1. Doing the integral with respect to y is going to give me x, y squared over 2, treating x like a constant. Substituting in y is equal to 0 and y is equal to 1 minus x is going to give me, let's take out that factor of 1/2. I've got x times 1 minus x all squared. We're multiplying that out. I'm going to have x times 1 minus 2x plus x squared, or x minus 2x squared plus x cubed. So doing the x integral is going to give me x squared over 2 minus 2x cubed over 3 plus x to the 4th over 4. So I'll have 1/2 of 1/2 minus 2/3 plus 1/4, which is equal to 1 over 24. So that's the mass. Let's have a look at the first moment about the y-axis, for example. So the first moment about the y-axis is going to be double integral over x times delta xy, dy dx. So the integral over x and y. We've got x, let's put in the density, so that's x times y, so I'll get my integrand is x squared times y. So carrying out the y integral again, from 0 to 1 minus x, which is going to give me, substituting that in, I can take out that factor of a half again to get x squared times 1 minus x all squared, which becomes integral of x squared minus 2x cubed plus x to the fourth doing the x integral is going to give me x cubed over 3 minus 2x to the fourth over 4 plus x to the fifth over 5 from 0 to 1. And if you put in those numbers, you'll get 1 over 60. Yep. So you can see that the case with non-uniform density, when we had density equals to x times y, did involve some slightly more complicated integrals. So we found that the mass is equal to 1 over 24, and we found that the first moment about the y-axis was 1 over 60. Now, I'd have to do the same calculation now for the first moment about the x-axis. But before I do that, let's see if I can make use of symmetry again, like we did in the first example, to try and figure out what that might be. So let's take a look at our region of integration. We've already seen that the region of integration is the same if I swap x and y. And we saw in the first example, when I had a uniform density, that meant that the first moment about the x-axis and the first moment about the y-axis were the same. And that meant that the x and y coordinates of the center of mass were the same. They have to be, because if I swap the x and y axes, I have to swap the x and y coordinates of the center of mass. The question now is, does this still apply when I've got a non-uniform density? Certainly the region of integration is the same. So the x and the y axes can be swapped to get exactly the same region of integration. It's just a triangle. The question is, does the density change if I swap the x and y axes? So if we take a look at the density, imagine if I was to rewrite x everywhere as y and rewrite y everywhere as x. In other words, is the density the same if I swap the x and y axes? And you can see that that is the case here. If I replaced x with y and y with x, I would get y times x, which is the same thing as x times y. So what I'm saying there is that replacing the x-axis with the y-axis and the y-axis with the x-axis doesn't change the region of integration and doesn't change the density. So there's nothing in this problem that will change if I change the x and the y-axes. That means that everything in the x direction has to be the same in the y direction. So the first moment has to be the same, and the x and the y coordinates of the center of mass have to be the same. So from symmetry then, that is the fact that I can replace x with y and y with x to get the same thing. I have that the first moment about the x-axis must be the same as the first moment about the y-axis. So we saw that that was 1 over 60, which means that the center of mass about the x-axis has to be the same as the center of mass about the y-axis. So what was that? Well, the center of mass about the x-axis was my over m. So that's 1 over 60 divided by 1 over 24, which is 24 over 60. And if I divide both by 12, I get 2 over 5. So the center of mass coordinates here are 2 over 5 2 over 5. So in this problem, we had to set up a whole bunch of double integrals, making sure to sketch the region of integration and determine the limits of integration. But the advantage here is that we could actually reuse those limits of integration again and again. In every single integral, they were the same because the region of integration was the same. Once I carried out those integrals, I could use symmetry of both the region of integration and the density to actually save myself some time. So in this case here, I managed to avoid having to calculate mx by using the fact that by symmetry, x and y can be swapped, which gives me that the first moment about the x-axis and the first moment about the y-axis are the same. Then I could calculate the center of mass coordinates. So we always have to be on the lookout for any symmetry in the problem that we can use to avoid having to do extra integrals. But remember, to use symmetry, I have to have symmetry in the region of integration and in the density. So I need to have both of those to be able to use symmetry. If I don't have both of them, I can't use symmetry, and I need to calculate all of the integrals separately. So let's take a look at another example, this time where we're going to also calculate the moment of inertia. And just like the center of mass coordinates, we're going to try and make use of symmetry whenever we can to simplify those integrals. Now, in these problems, for the rest of this lecture, I'm going to set up the integrals for you, and I expect you to try and calculate those integrals yourselves. So in example 2, we're going to look for the mass, the center of mass, and the moment of inertia about the y-axis of a thin plate bounded by these curves with a density given by this expression here. So we need to calculate we need to first of all sketch the region of integration. That's our first step here. So let's sketch the x and the y-axes. Here's y, here's x. We're sketching the curves y is equal to x squared. Well, that's fairly straightforward. That's a quadratic that looks something like this. And we're also going to need to sketch y is equal to 2x minus x squared, and it's useful to look for the roots of that. So let's pull out a common factor of x. So we're going to have y is equal to x times 2 minus x, which means that this thing has roots at x equals to 0 and x is equal to 2. And it's going to be a hill rather than a valley because it's got a minus sign in front of the x. So it's going to do something like this. So it intersects at x is equal to 0 and x is equal to 2. And again, this is the curve y equals to 2x minus x squared, which we've factorized as x times 2 minus x. Okay, we'd like to be able to find the point of intersection of these two curves. Obviously, there's going to be a point of intersection at 0, 0. But there's also going to be a point of intersection over here. So let's find that point of intersection. So we've got when y is equal to x squared, and it's also equals to 2x minus x squared, we find that 2x squared is equal to 2x, or x squared minus x is equal to 0, which means we have roots at x, and x is equal to 1. X is equal to 0, y is equal to 0, and x is equal to 1, y is equal to 1. So I can obviously substitute in those values of x I've found into either of these two, and they'll both give me the points 0, 0 and 1, 1. So the region of integration is clearly this region here. And if we're going to make use of symmetry in this problem, we're going to have to think about whether or not this region of integration and the density are symmetric under exchange of x and y. So let's take a look at the density. It's given by this formula here. If I was to swap x with y and y with x, would I get the same expression for the density? And you can see that if I replaced x with y, my density would then be y plus 1, which is not the same. So this is not symmetric with respect to x being replaced with y and vice versa. So unfortunately, I'm not going to be able to make use of symmetry in this problem. Likewise, if I was to look at this region of integration, it's not at all obvious just by looking at it that exchanging x with y would actually give me the same region of integration. So symmetry can't be used in this problem. So let's set up the integrals anyhow. We're looking for the mass. To do that, we're going to need my region of integration, so let's take a look at that. So what we're going to do is we're going to take x between 0 and 1. For a given value of x, we're going to have to start at y is equal to x squared and integrate until we get to y is equal to 2x minus x squared. So my limits of integration then which define the region are given by x going between 0 and 1 and y going between x squared and 2x minus x squared. Now I chose here to do x as my outer integral and y as my inner integral, and the reason I did that was because I have simple expressions for y in terms of x at the lower bound and the upper bound for the inner integral. If I wanted to do it the other way around, I'd need to have expressions for x in terms of y, and it's not immediately obvious how I would do that. So this is a much easier integral to do, going from x as my outer integral and y as my inner integral. So let's set up the mass integral. That's going to be the double integral over the region of integration of the density times the area. So that becomes the integral from 0 to 1. Y goes from x squared to 2x minus x squared. The density is given by x plus 1, and we're doing the y integral first and then the x integral. So I'll leave you to do that double integral. I'll just give you the answer. It's equal to 1/2. The mass, the first moment about the y-axis, let's write down the formula. Integral over the region of integration times x times the density times the infinitesimal area. So we've got the integral from 0 to 1, integral from x squared to 2x minus x squared of x times x plus 1 dy dx. And again, I'm not going to do that integral. I'll leave that for you to do. And that's going to be given by 4 over 15. Finally, we've got the first moment about the x-axis. So that's given by y times the density, dA. So that'll be the integral from 0 to 1, integral from x squared to 2x minus x squared of y times x plus 1 dy dx. And when you do that integral, you'll find that that actually also is 4 over 15. So just by coincidence here, the first moment about the y-axis and the first moment about the x-axis are both the same. Now, we couldn't have anticipated that in advance because we saw that this density was not symmetric and the shape was not symmetric. So in fact, these things are not symmetric in the same way somehow, but again, we couldn't have figured that out in advance. We'd have to have actually done the integrals. So once I have the integrals my and mx, I can calculate the center of mass coordinates. So that's my over m. So that's going to be 4 over 15 divided by 2, or 2 over 15. And the center of mass coordinate in the y direction will actually be the same as well. 2 over 15. Sorry, 8 over 15. So dividing by half, multiplying by 2. So those are the center of mass coordinates. Now let's take a look at the moment of inertia. Now we're asked to calculate the moment of inertia about the y-axis. So let's write down the formula for that. Again, set up the integrals. So the moment of inertia about the y-axis is given by the double integral over the region of integration of x squared delta xy dA. So again, we notice that the subscript here refers to the axis, and we're actually going to put in the distance from that axis in the integral. So we've got x squared here, but a subscript y. So slightly confusing, but that's just referring to the distance from the axis y. So what do I get then? So putting in my limits of integration, integral from 0 to 1, integral from x squared to 2x minus x squared times x squared, x plus 1. You can see that this is going to be another integral we can do, and I'll give you the solution. It's given by 1/6. So again, I'm going to leave you to do those integrals and confirm those numbers. We found that the mass was 1/2 mass units. The first moment about the y-axis and the x-axis were the same, and that gave us the x and y coordinates of the center of mass being the same. And then the final calculation was of the moment of inertia about the y-axis. That involved an integral over x squared times the density. And we found that this was 1/6. And that tells us how this object resists rotation about the y-axis. So let's look at one last example now, example 3. We're looking for the mass, the center of mass of a lamina, or a thin plate, bounded by y is equal to 1 minus x squared in the x-axis, and we're going to look at 3 different cases: when the density is uniform, when we've got a variable density given by delta xy is equal to y, and we've got a variable density given by delta xy is equal to r. And we're going to try and make use of symmetry here whenever we can. So let's take a look at what this lamina is. Well, bear in mind now that we're looking at a lamina bounded by y is equal to 1 minus x squared, which if I square both sides of that, actually just turns into the unit circle. So we've got something that's bounded by the unit circle above and by the x-axis below. So we're going to have a semicircular region of integration. So let's sketch. There's my unit circle. Here's my x-axis. So the region of integration is shown in green here. And you can see, because of the symmetry of this region of integration, that polar coordinates are going to make life much simpler here. So we're going to express these integrals in terms of polar coordinates. So what are the limits of integration of this shape? Well, you can see that theta is going to be going from 0 to pi, so 0 to 180 degrees, and r is going to go from 0, the origin, to 1, the unit circle. So those are our limits of integration. Let's now set up my integral. So I've got the mass is given by the double integral over the region of integration of the density. So let's look at the three different cases. We've got the integral. We're going to do theta first, or theta is the outer integral, r is the inner integral. My density in this case, for the uniform density case, is just 1. And remember that dA for polar coordinates is r dr d theta. So this is the case when we have uniform density, and you'll find that the mass in that case is simply pi over 2. So this is the case of uniform density, A. Or we could do the same integral, but have a density given by, so this was the case of delta equals 1. In this case, we're going to look at delta is equal to y. And remember that we're using polar coordinates here, so I need to use the polar coordinate representation for y. So let's put that in. We're going to have r sine theta times r dr d theta. So again, I've replaced delta equals y here with its polar coordinate representation, and I'll let you show that that is equal to 2/3. And the third possibility is integral from 0 to pi, integral from 0 to 1 of r. So that's already in polar coordinates. And you can show that the mass in that case is a half. So this was case C, when delta is equal to r. So it depends, it gets more dense as you move further out from the origin. So those are the three different cases: uniform density, density depending on y, and density as a function of r for the mass. So let's take a look at the moments of inertia. Sorry, the first moments. So my, remember that was the double integral over omega delta xy times x times the infinitesimal area. So for the uniform density case, we're going to have 0 to 1, 0 to pi, 0 to 1. Remembering that x is equal to r cosine of theta. And delta xy in the uniform density case is 1. And dA is r dr d theta. So this is case A. Delta is equal to 1. And I'll let you show that this integral becomes y, 0. We have the case of the density being equals to y. So this is case B. So x is still r cosine of theta. We've got delta is equal to y, so r sine of theta, r dr d theta. So this is x. This is delta, which is equal to y. And in this case, we also get 0. So this was the case of delta is equal to y. And the last case was when delta is equal to r. So here x is equal to r cosine of theta, delta is equal to r, and the integral in this case is equal to 0. So you notice something interesting here. In every single case here, the moment about the y-axis is equal to 0. So that was for a uniform density, a density that depends upon y, and a density that depends upon r. Now let's have a look and see if we can think about how we might have anticipated that based on our region of integration and on the density. So the region of integration here is clearly got some symmetry between left and right. It's got some symmetry if I rotate it about the y-axis. So the question then is there as much mass on the left-hand side of this object as there is on the right-hand side? Have I got the same lever force pushing it on the y-axis to one side as I do a lever force pushing it about the y-axis towards the other direction? Now for a uniform density, that's very clearly the case. It's almost like I've got a seesaw here with exactly the same amount of weight on one side as I have on the other side, so the seesaw is perfectly balanced. So there's no net lever force. There's no moment. But what about the case when I've got variable densities? I've got a density that depends upon y, or I have a density that depends on the distance from the origin. Again, do I end up getting the same amount of lever force about the y-axis on the right-hand side as I do on the left-hand side? Well, if the density depends upon y, then what that's telling me is that I've got an increasing mass as I move up this direction. So there's basically zero mass down here. It's increasing, 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 until at the very top I've got the highest mass, a density of just 1. But you can see that that's evenly distributed left and right, because it only depends upon y. So the density here doesn't depend upon x, which means the mass on the right-hand side has to be the mass on the left-hand side, so they perfectly balance about the y-axis. So it actually has a 0 net lever force, a net moment about the y-axis. The same goes for the last case, where the density depends on the distance from the origin. You can see that, yes, it does depend on the distance from the origin, but it also is the same left as right. So it's like a mirror image left to right. So the same amount of mass is on the left as the same amount of mass is on the right. So the total lever force is 0. So my is equal to 0 for all 3 of these cases. Again, we might not have anticipated that, but in retrospect, it does make sense. Now we need to take a look at the lever force, or the first moment, about the x-axis. And we don't expect these to go to 0 because we're looking at tilting or rotation about the purple line here. So basically, is this thing going to tilt backwards or forwards? And it definitely will, because there's not an even amount of mass on top and bottom. So let's set up those integrals. We're looking for the first moment about the x-axis. It's going to be given by a double integral over the region of integration of the distance from the x-axis, so that's y, times delta xy dA. And we're going to be expressing everything in terms of polar coordinates, so we're going to be making use of y is equal to sine theta, and we're also going to be making use of the fact that my density can be expressed in terms of polar coordinates. So let's look at the uniform density case. Integral from 0 to pi, integral from 0 to 1 of y times the density is 1 r dr d theta, and you can show that that is equal to 2/3. So this is the case of delta is equal to 1. Let's look at the variable density case b. So y again is r sine theta. The density in this case is also y, so r sine theta, r dr d theta. So here I've used r sine theta is equal to y, and the density is equal to y, is equal to r sine theta. So carrying out that integral, you'll find that the moment of inertia, the first moment about the x-axis is pi over 8. Last one, integral from 0 to pi, integral from 0 to 1 of y, so r sine theta, times r. The density here is r. And I can't forget that extra factor of r in dA. So you can calculate that, and you'll find that you get mx is equal to 1/2. So this was case B, delta is equal to y, and case C, delta is equal to r. So that then gives us our coordinates of the center of mass in the three cases. So let's look at the three cases, just using my over m, mx over m. So we're going to find that in the uniform density case we get 0, 4 over 3 pi. In the case when the density is equal to y, we get 0, 3 pi over 16. And in the case when the density is equal to r, we get 0, 3 over 2 pi. So in all three of those cases, we find that the x-coordinate of the center of mass is equal to 0. In other words, it's right in the middle of our object here. It's right in the middle. And that makes sense because, again, this thing has a mirror symmetry, left-right. So we have an object now that has a center of mass that depends on the density, but the x-coordinate is always 0. So we found it's always going to be somewhere in the middle here. Now, I do encourage you to try and calculate what those double integrals are. It'll give you more practice in calculating these and hopefully finding some speedy ways of doing polar integrals. And it'll also give you some practice dealing with some quadratic terms. Like, for example, here you've got sine times sine, so you'll have sine squared theta, and you'll need to evaluate that using the double angle formula. Likewise, here you've got cosine times sine, so you're going to have to use a double angle formula for that as well.